Hi, everyone. Thank you for being here. It's my pleasure to welcome Galit Yom-Tov, who's be giving today's SNAPP seminar. She's an associate professor at the Industrial Engineering and Management faculty of the Technion. Her research focuses on the operations of service systems, in particular healthcare and contact centers. She's also the co-director of the C-Lab, which is a worldwide hub for research and teaching in service engineering. Her research, as you will see even in today's talk, is pretty multidisciplinary. So she combines tools from data science, from stochastic modeling, and even psychology in her work. And she's published in all the leading journals of our field. And she's also serving as an associate editor for MSOM and OR. Galit, it's a pleasure to have you, and the floor is yours.
Okay. Thank you. Thank you for inviting me. It's really a pleasure to be here. Okay. So what I'm going to talk today is a paper that I'm really excited about, because it's really, like you said, combining everything that I believe in, which is, first of all, using data in order to understand how service system works. And this is, I think, a very good example of that. And my view that you should not only look at, I would say, on the mathematics, but also try to combine in the mathematics insights that are coming from psychology about what are the interaction or the interplay within a service system that has people both on the side of the customer and the side of the agent. And so today I'm going to talk about the paper that we call the co-production of service, in which we are basically proposing a new way to model service time for contact centers specifically. And we are going to do that using Hawk's processes. And this is joint work with Andrew Doe, who is here, also Antonio Castellanos, who was my PhD and is now in Booth working with Amy, and Jamal Pender from Cornell, and Leo Gudlinger, who used to work in Live Person, and they provided us the data that I will use in this paper, in this presentation. Okay. So why contact centers? So the first reason that I'm really interested in contact centers is that, well, they're all around us. So people are using more and more text in order to communicate between one another. We see that when we are looking at our WhatsApps all the time, but especially since COVID, we see that also more and more in service systems where people are talking with organizations and not just between themselves. And this offers organizations a lot of advantages of reaching out to a lot of people that may be far away and not necessarily need to come to them in practice, physically, but also give the companies new ways to reach people and to manage their organization, in the sense that papers were showing, for example, that small sellers in Alibaba can increase their sales by 16% if they are offering chats as a way to communicate between those small sellers and the customers around the world. I have a paper showing that companies can actually triple their sales if they are looking or monitoring at the activities of the customers on sales websites and targeting the specific customers that they need to reach out to and offer them service. And so this really helping different companies to make more money. And so we see that the use of contact center growing and growing around the world. The third reason is data. Nowadays, we were fortunate in the last, I would say, 4 or 5 years, more 5, 6 years, to get multiple data sets to our C-Lab from so far 3 companies. that are enabling us not just to look at the service system in general, but to dig into the interaction between customer and agent. And that's because the data that we have on contact center is on completely different level of granularity. Instead of just saying service started and service ends, we know exactly what happens within the interaction. We know what each person exactly wrote. And so we have a full transcript of the conversation itself. And therefore, we can learn much more about what's happening within a service interaction. The fourth reason is operational. Contact centers are actually needs many things or methods that are different from call centers. Parameter estimation and performance evaluation is different. Staffing is somewhat the same. Concurrency is also very, very common. So each agent is serving multiple customers. Today, I'm going to talk about how routing and conversation closure needs to be changed or looked at. And this is something that is a little bit different from other environments. So if I'm looking at this very, very general schema of things, people are arriving, right, meaning they're writing some text in the text application and reaching out to the company. The company would put them in a queue, waiting for some agent. And then if they survive the waiting time, they would start chat, meaning that they would write something, the agent would write something, the customer would write something, and they will have back and forth messages. And then the service would end, and sometimes we'll send the customer some kind of survey about the service. And so if I'm taking a general view of things that we've done on contact centers, so we looked at optimization of proactive invitation policies. We looked at the behavior of silent abandonment of customers waiting in the queue in contact centers. We looked at the text that customers and the agents are showing and developing something that we call emotional load, basically showing that the language that the customer and agents are using is influencing one another and the efficiency of the system. We can use that sentiment in order to evaluate the performance or the satisfaction of the customers. We can look at problems like staffing, concurrency, routing, and closure, which are what we are going to talk today. And today, I'm going to concentrate specifically on modeling the service time and how would that reflect in the routing. So this is the general scheme. There is a lot of very, very interesting problems, and I'll go and dig into the one. Okay, so our goals today is basically to build a model for the a stochastic model for the service type in contact center, then use that model in order to understand the impact of co-production on the service system. Then we are going to look at improving performance by changing the routing policy in a way that would take the rule of the routing from the Hawks process, from the model of the service time that I'm going to present. And I'm going to introduce the connection between the routing problem and the new problem that we call the closure problem of conversations. Okay. So I'm going to start with something that we all know, but we usually ignore. And that's the fact that service time is not exogenous. It's not that someone is coming from home and have service time and that's it. But what happens in the system, whether it's the load on the agent or the way that the agent is reacting, is also changing the service time. And specifically in the context of contact centers, was shown already that the following four factors are impacting service time. For example, the concurrency, the fact that each agent is treating at the same time multiple customers is of course changing the duration of the conversation, because when the agent is writing to one person, he cannot write to another person at the same time. So the other person is waiting for some time within the duration of his conversation. Moreover, it's not just that he needs to wait until the agent is ready. The fact that the agent is jumping between conversation is also a cognitive load on him, and therefore his reaction time is increasing, mistakes are also increasing, etc. And so the fact that we have concurrency is increasing or changing the length of stay. Another factor that we needed to take into account is what I mentioned, sentiment or emotional load. Basically, what I showed with two PhD students of mine, Daniel Altman and Shelly Ashtar, is that the language that customers and agents are using is influencing one on the other, and the language that the customers are using is changing the time that the agent is reacting and the number of words and messages that he's using. So directly affecting the length of stay of the customer. Also, within each message, there is concrete information, not just sentiment, but concrete information that each party needs to read, process, and react to. And therefore, as we have more information, we have longer lengths of stay. So this is also a factor that is changing the duration. And this concept is coming into play in the heading of this talk, where I talked about co-production. So the co-production concept is basically acknowledging that when we have a service interaction, we have information exchange between the two parties, and both parties need basically to collaborate in order to achieve a good service. So a good service is not just a very professional agent, but it's also a very, I would say, in the moment and articulate customer that is also contributing to the success of the service. The last factor is just in terms of reciprocity of service, I would say reaction times. It was shown by Ilke et al. That if a customer is waiting, then the customer response time would increase, etc. And through all those examples, what we see is that we have a very complicated environment, because the decisions that we make, the operational decisions that we make about concurrency impact the agent, which would impact the customer, which would in turn would impact the agent again. And so we have something that is very, very complicated. And the question is, whether we can actually have some kind of a comprehensive model that would take all those things into account, both the role of the customer and the role of the agent and the role of the system in creating service and creating this construct that we are used to call service time. And so the first thing that that I do usually is not just think about it conceptually, but one of the reasons that we have the C-Lab is that we will be able to look at data and how things are in reality, very much like physicians would look at the world, do experiment, and get this data and try to fit a model to the data. And so in a contact center, basically, it's very much like I showed you before, but we have multiple agents, and each agent is taking into account multiple customers, or taking care of, sorry, not into account, taking care of multiple customers at the same time. And so if I'm taking this from the concept to the data, then the data looks something like this. So this is real data of one specific agent treating 7 customers between 5 o'clock until 6 in the afternoon. And each dot that we have here is a message. Okay, and the first thing that I want us to do is basically look at this data and think, what do we see here? So the first thing that we saw here was that there are a lot of bursts of activities. So the conversation is not something that is very, very well ordered. It has bursts and then a few minutes break, stop, bursts and a break, bursts and a break. Sometimes the break is long. Sometimes the break is very, very long, more than an hour. But it's not very well, I would say, ordered. The second thing that we see is basically those very, very long breaks. And if we are, for example, taking slices of 1 minute from each conversation, and we ask ourselves within that minute whether there are messages or not, what we would find is that in 70% of those minutes, basically there is no interaction. No one is active in the conversations. So those long breaks that we see is actually very, very common in the data that we have. And the reason for that is twofold. First, the agent itself is treating multiple customers at the same time. So for example, if the agent is answering customer number 4, then he cannot answer customer number 2. So at the same time, customer number 2 needs to wait, and therefore to the agent, and therefore we see here a break. But when he comes back to the customer, maybe the customer is not there anymore. Maybe he went to eat lunch, maybe he went to someone to do something else. And so we would see those long breaks. Maybe those breaks are something that the customer is, I don't know, need to check. Okay, need to check something, his account or log in or whatever. Maybe he got something. And so to do. And so those breaks could be because of the agent, and they could be also because of the customers. We don't know actually who caused them, but it's both from outside the system or inside the system. The third thing that we see is the fact that the conversation is asynchronous. And in that we mean not just the fact that we have concurrency and therefore the agent is jumping between conversations, but also that it's not the way that we think about it. It's not customer writes something, agent writes something, customer writes something, agent writes something, very, very orderly. But what we see is more something like this. Agent writes few messages, then the customer, then the agent, then the customer. Sometimes it's one message, one long message, and sometimes it's multiple short or long messages, or a message that is divided to multiple lines. And we'll refer to this phenomena with the terms of self and cross-excitation. So self-excitation is when the agent or one side is writing multiple messages one after the other. And cross-excitation is when the roles are flipping, when one side wrote a message and then the other side answered him, like what we have, this flip here and the flip here. Okay. What else do we see is that both sides are providing information. So we have like those Q&A sessions within a conversation. The agent is asking a question, then the customer is answering. The customer is asking a question or have a request, and then the agent is answering. And therefore, and this is what we talked about before, the co-production in which each side is contribute information. And this concept was very well defined many years ago. For example, I'm giving you here the quote from Fudge, that the productivity of many service systems depends in part on the knowledge, experience, and motivation of the customer, not just the experience of the agent. And because of this dependencies is not always good, we see a trend in the industry of moving from co-production or from services that are either in contact centers or in general to what is more sometimes referred to as self-production. So things that the customer are able to do on their own without the agent. So some companies are trying to move the customers to do things on their own. For example, we are now doing transactions in an application in a bank and stuff like that. And some of them at the same time would offer customer different types or different modes of communication. For example, everyone here knows how complicated it is to do tax returns in the US. And so you could have a help that is co-production. So as you fill your tax report, someone is helping you in live to do it correctly, or you can do it in self-production, but in this case, it's self-production of the company. You just send your material, and someone in the company would fill everything and go back to you just to click send. Okay, so you can do things together, or you can do things just one side is doing most of the work. Okay, so we want a model that would be able to capture this, I would say, this range of operational modes between everything is done in collaboration, or maybe things are done more by one side versus the other. Okay. Okay, so the way that we are going to do that is that we are going to look at the interaction between customer and agent and build a stochastic process that would model that interaction in a dynamic way. So as the process is evolving, I want it to change in a way. And we are going to do that by assuming or treating the conversation as homogeneous and changing over time. So it's changing over time as each person is changing its behavior. And this is in contrast to the classical models that are basically looking at the service time as something that is built from different activities. For example, some of you probably know the paper of Mandelbaum and Breman that look at service as a network of activities, and therefore service time is basically a phase-type distribution. Or also very common is to look at the service as a Jackson network. For example, this is from a paper of Campello that look at the service time as a re-entering network. And we are going to use those ideas in order to create a baseline that we are going to compare our model to. So basically our two baseline are going to be models that are looking at this service interaction and assume that the times so each message is an event in our stochastic process. And we're going to assume that either those events are taken from a static exponential distribution, very much like a static Poisson process, or we are going to assume that there is some kind of time variability here. Maybe the rate in which conversations are progressing in the beginning is different than in the middle and different in the end, just because we have different tasks in the beginning, middle, of the end. For example, in the beginning, we are busy in introduction. In the middle, we are busy in first in Q&A, understanding the problem, then solving the problem. In the end, more of thank you and goodbye. And so maybe those are having different rates. So basically, we're going to have two baseline models that are inspired by those activity networks and jet networks approach to how to model service time. In contrast to those, we're going to propose to use instead Hawk's processes. So for those of you who don't remember or don't know what Hawk's processes are, basically Hawk's processes were proposed by Hawks in the 70s in order to model earthquakes. So we know that after an earthquake, the probability of having another earthquake is very, very high. But as times go by and we did not have any seismology activity, then the probability of having an earthquake is reducing. And so in order to model this type of activity, what he proposed is to have a process in which the rate of activity is basically jumping when we have an activity, and then over time it decays. And whenever we have an activity, it jumps and then decays again. And so the rate at any specific time depends on the history of the process, because it's a sum of those decades, jumps that happens in the history. And this was proved to be very good for, as I said, earthquake, but also for finance and tweeting and retweeting and in many, many applications. And so we are going to use it also here. And so what we're going to propose is basically two-dimensional Hawk's process. The two dimensions are basically the two roles. So one dimension would be the agent and the other dimension would be the customer. And then we'll have within the process also self-excitation, where each role is increasing its rates according to his own activities. And cross-excitation would be each person is impacting the other person activity when he writes something. The reason that it's very natural to use Hawk's processes is exactly the first observation that we had in the data of those bursts of activities and then dormant times. So Hawk's processes are really a natural way to capture this in a really elegant way. So this is the model. In the paper, we have 3 models. I would only show you here 2. So what we call the bivariate Hawk's process model is basically saying that we have 2 correspondence rate, one for the customer, one for the agent, and the customer correspondence rate depends on the history of the messages that the customer wrote and the history of the messages that the agent wrote. And basically, whenever we have a message, we have a jump in the size of alpha and then a decay in the rate of beta. And each of the directions of those 4 directions of the conversation is jumping and decaying in a different rate. But altogether, we are getting this process that I talked about, a 2-dimensional with the roles that have both self-excitation and cross-excitation rates. So the assumptions here is that each conversation is basically independent of what's going on in the system and is looked at as a Hawk's cluster. So it's a finite process, a finite stochastic process, where the rates depends on the history. Each side may have different rates, but each side is influencing the other side. And using this kind of a process, we can learn many things about what's going on in the conversation. We can learn, for example, about how each side is influencing the other side. We can learn who drives the conversation by comparing for example, how many on average, this alpha over beta is basically the average number of messages that the customer is writing as a result of the agent writing. So, and if I'm comparing how many messages the customer write as in response to the agent to the number of agent messages in response to the customer, I can ask myself basically who is more active or who is more responsive to the other, and basically claim that whoever is bigger is the one who is driving the conversation forward. Another thing that I can learn, again, by comparing those alpha over betas, is ask myself whether those conversations are more co-productive or more self-productive. So if those terms of co-production, which are the cross-excitation, are stronger than the terms of the self-excitation, then I would say that this process is more co-productive. There is more dependency between the two roles. But if the other way, then I would say that it's more self-productive because each one is working separately. Any questions? No? Okay.
Galit, I had a quick question, if you don't mind.
Yeah.
So I was just wondering, in this model here, how would you measure or take into account this concurrency? For example, if the agent is talking to several customers, I guess that goes into this A, right? Because then it's like the
so this is the next slide.
Oh, okay. Good.
Okay. So I would say a more sophisticated model is, instead of saying that those jumps are just constants, I would say that those jumps depends on the behavior of the agent and the customer, and depends on the concurrency. The concurrency is here, K. So we would have basically random jumps, because here we are taking into account basically sentiment in the number of words. And because each of one is a random variable, basically we have random jumps for the customer and the agent. And we are taking here into account, through those jumps, both the sentiment and how it's impact each one, the number of words, basically the amount of information that each one is providing, and the concurrency. So the concurrency is basically only influencing directly the agent, and would influence the customer only through its impact on the agent. And the way that we modeled it is that basically we are saying that as concurrency increases, the process is kind of becoming longer and longer. So it's expanding over time. So we would have longer process as K is increasing. Does this answer your question? So the difference between the BHP here and the CIS BHP is that it takes into account the system parameters and basically the concurrency. But then instead of having a host cluster, what we have is a marked host cluster, because those jumps are becoming random variables. Okay. More questions? No? Okay. Okay, so we have those very, very nice models. And then the question is, first, what we can say about them. So our first mathematical result was to look at this CIS BHP model and try to see when is it stable, meaning when is the service time is finite. And what we see is interesting on its own. Basically, what we see is that the stability depends on the connection between the cross-excitation rates and the self-excitation rates. Basically, if the system has high cross-excitation rate, if I need a lot of back and forth in order to complete the service, then I cannot have a lot of self-excitation. So those needs to be close to zero, and vice versa. If I have a lot of excitation rate, so if I have a lot of self-production, then at least one of those directions needs to be low. Okay. The next thing that we did was trying to see whether this model holds water and is better than other models. And so for that, we take data. So we took data, 1 month of data from LivePerson. That's a company that is building infrastructures for contact centers. And we took from a very big
can
company.
I ask you a quick question
Sure.
on your theorem 1 before you move on? It was a sufficient condition, not sufficient and necessary, right? Do you have any sense about the necessary way?
No. Andrew, do you have any intuition?
Yeah, the short answer is no, not really. So the this result is built on like more general stability conditions for hawks that are using like an eigenspectrum of a particular matrix where these alpha over beta show up, and those are also sufficient, not necessary conditions. So we would need to go deeper into the well. This seems to be the typical case here, but I don't have a satisfactory answer there. It's an interesting question, but I don't think we have a great one for it yet, or a great answer for it yet.
Cool, thanks.
Yeah.
Yes. Yes, David.
So I guess this condition's about like long run stability, right?
Mm-hmm.
So I mean, for a system that's self-exciting like that, is it obvious that something much more awful doesn't occur, like explosion in finite time, or like
Explosion from time.
like I mean, if it was self-exciting enough, it would blow up in finite time, right? It wouldn't even be well defined, I guess. Is that
Yeah.
So I'm just a little confused about like, could you go back to the definition in terms of G of what these alphas and betas are?
What these alpha and betas are. So
Maybe I got confused.
alpha is the jump and beta is the decay.
So there's no G history function as part of this theorem one.
The G history function is like a e to the negative beta.
Yeah. So basically, okay, in the paper, we are more defining it as F times G in a way that we unified all the models that we have together. And basically, this is the G and this is the F.
I see. Okay, so this is a specific type of G. Okay, so I guess probably for this, you can't get explosion, but for general G, you probably could have it do something very bad, I guess, right? Like,
yeah, we only look at exponential decays. We did not try any other types of kernels.
So okay. So maybe just is there, just looking at these equations, how do we interpret this as far as what stability would mean? Like, I understand it's coming from some matrix eigenvalues, but what's the common sense reading of these equations? Like, is it the bigger it gets, is there a mean reversion? Like, I'm just, yeah, how do we think about that just at a high level? Because I realized I was thinking about a general history dependence and I don't know how to interpret these equations. Yeah.
So for me, stability, I mean, okay, I don't know of any conversation that would be exploding, right? So service times or service systems in general, or I would say, sorry, service conversations, and that's what we're looking here. In practice, you would not see any explosion of any type.
In Chat GPT universe, is that obvious? I mean, again, I'm not saying it's practically relevant. I was asking it from a totally theoretical, just trying to understand the equations.
Galit, if you go to the stability condition, Dave, I think the answer to your question is that this is more than, or actually, rather than system stability, this is like conversation stability. So this does actually guarantee what you want, because we've got that the number of messages is finite almost surely. So you don't have any of those explosion, then that's the limiting number of messages as time goes on. So we have a finite conversation, which is what I think Galit is saying.
I misunderstood. So you're saying under these conditions, it actually it's not like a steady state conversation, it just literally dies.
It literally dies, and then more and more
time.
Conversations come into the system. Yeah, exactly.
I see. Is there?
It's a finite process, basically.
I see. Okay.
It's a Hawks cluster.
I see. I didn't.
Okay, it's a finite process.
Thank you. That's
okay.
I'll be quiet now.
Yeah. Okay, so we want to see in practice, that this models is better than our benchmark or other things that we can think of. Okay, and so we took this data and we divided it into two parts. So part in which the training set, in which we are estimating the parameters, and a part which is our test data, in which we are testing the processes, or we are testing the accuracy of these processes on that test data. And this is the accuracy results in the paper. Okay, so what do we have here? So basically what we have here is two measures of accuracy, one looking at the total duration of the conversation, and the other one is looking at the gaps between messages. And what we are showing here is the difference between the data CDF and the CDF of the model. Okay, so we are estimating the parameters using the training data. We get parameters, then we simulated conversations with these parameters and got distribution of conversations with these parameters of those different processes. And then we are looking at the differences between that distribution and the distribution of the data in the training set, in the test sets. Okay. And then we have different ways to measure the accuracy of the model. So as this is closer to this horizontal line in 0, that this means that the model is more accurate. And so we measure the goodness of fit using in 3 ways, using Kolbomov, Smirnov, and one W1 measurements in terms of the distance between those CDFs. And we also developed in the paper, I will not go into it, a new goodness of fit test that is based on residual analysis. But this is only available due to, it's very, very complicated, only for the UHP model. So only if we are not taking into account the roles, but only the history. Okay, so here I will not talk about it, even though it's very interesting, but only present those two performance measures. Okay, and what we see when we compare the benchmark, which is the either static Poisson or time varying Poisson, to the Hawks that are basically based on the history of the conversation, is that we see a huge gap in terms of accuracy, both in the duration and the gap distribution, where it seems to be that something very, very essential could not be captured by a simple Poisson process, or not even a time-varying Poisson process, but is being able to capture by any of our Hawks process variations. And that is basically the fact that the process, as it goes along, is changing its dynamics according to the history. And something else that we observe is that if we want to capture very accurately, specifically the gaps, then it has advantage also to take into account the concurrency and the sentiment and the number of words. Okay, so we have here a little bit better in the gaps, specifically for the CSPHP. Okay, and estimating those parameters, we can try to get insight about how the process is changing. For example, due to short time, I would just skip or maybe on one specific fact. That our specific process seems to have, I would say, more car production than self-production, and the person who is driving the conversation seems to be the customer. Okay, so what can we do with such a model? So we have in the paper actually 2 usages. Since I have only 15 minutes, then I'll only be able to talk about routing. And so what do we do here? Basically, the idea is to look at those very, very long periods of time and identify something or a situation where the classical routing is basically failing. Why do I go back to this figure? Is let's think of, for example, what happens at 6 o'clock in the afternoon. The agent has 4 conversations that are assigned to him, 1, 2, 3, and 5. While in practice, those 1, 2, 3 are actually not active, but number 5 is. So the fact that we have those long breaks means that the number of active conversations is not the same thing as the number of assigned conversations. And actually, if we are looking at the distribution of assigned conversations, this is what we see here. And we look at the number of active conversation, the number of active conversation is way, way skewed to the left than the number of assigned conversations. And so if I'm just deciding on my routing according to the assigned conversation, I could think that at 6 o'clock, this agent is busy with 4 conversations, which is definitely enough, while in practice is not busy at all. And so this could be a problem. So what could think of, okay, so instead of having concurrency 4, why not just, put concurrency 6? That's one way to solve this problem of many inactive conversations. But what we are going to suggest is something else. What we are suggesting is that instead, when we are looking at a specific time when we need to assign a new conversation to an agent, and we have 2 agents that have the same number of conversations, instead of just randomly choose one, what we'll do is we're going to use the Hawks process and ask ourselves for each of those conversations, what is the probability that this conversation would have an activity in the next, let's say, 10 minutes, and then choose the agent that has the lowest number of expected activity. And so formally, what we are going to calculate is this measure, the number of messages that would be between T0 and T for some T that we would choose, and basically choose the agent that has the lowest expected number of messages. And when we do that, we are basically moving from the classical lightest load policy that was suggested by many researchers for this specific context of multiple of system with concurrency. Okay, so this was used, this type of policy for healthcare, and Sakat and Zhang and Liu and Zhang for contact centers. So this was specifically designed for contact center policies. And we are going to basically say that instead of using the lowest load, we are doing this very, very small modification, which we call lowest load plus hogs, in which on the first level, we are going to use the lightest load, meaning the lowest number of concurrency. And only if we have multiple agents with the same concurrency, then we are going to use the hogs in order to choose between them according to this measure. Is this clear? Okay. And what surprised us is how well it works. So here we see the outer weight, meaning the weight before you start service in the queue. And this is the inner weight, that's the weights that you have between messages because the agent is busy with other customers, okay? So this is the inner weight due to concurrency, and this is the outer weight due to in case that no agent is available. And what we see is that any of the Hawks processes is performing way, way better than the lowest load. The improvement is between, I don't know, 2 to 10% in this specific setting. And on average, it's improvement of 11% in the outer weight. And at the same time, so simultaneously, we see improvement also in the inner weight. So it's not, we usually think of inner weight and outer weight as something that as a trade-off. If I'm increasing concurrency, my outer weight is decreasing, but my inner weight is increasing, and vice versa. What we see here is by changing the routing and choosing wisely between those agents, we can actually improve both. Not only the average inner weight and average outer weight, but also we are able to increase the variance in those weights. And the question is why? Because the lowest load was shown to be asymptotically optimal for contact centers. So how come we are able to improve so much on that policy? So our next stage was to try really to understand why is the lowest load failing. And for that, we need to go back again to this, to the data and think of what's going on here. So what's going on here is that we have all those long, very, very long breaks. And those long breaks are something that the Hawks is actually able to capture, okay? And is able to capture in real time. And this is actually very, very powerful. And to show that analytically, what we did is something else. We think of those long breaks as very, very similar to the periods in the end of the conversation. And why is that? Because in both of them, what happens is that the Hawks process rate is basically reducing to be very, very low. If for a very, very long time, there were no activity in this conversation, then the correspondence rate for that specific conversation would be very, very low. And this is the case where the conversation actually ended here and only were closed here, but would also be for a conversation when it was dormant, but then started again. And so instead of looking at breaks in conversations, what we are going to look is at the end of conversation, at the closure of conversations, and looking at the new performance measure that we call success probability. And that is the case where conversation needs to be closed. And we ask ourselves whether it was closed before time or at the right time. For example, think of the difference between customer 1, 2, and 3. If I would close the conversation, let's say, at after 10 minutes that it was not active, for customer 3 and customer 2, everything would be okay. So the fact that I closed the conversation early would be fine. But for customer 1, the fact that I closed only after 10 minutes would mean that I actually missed that customer. So how I close the conversations is creating, or I can measure whether it was too early or on time according to that process. And so what we are suggesting is to extend the routing problem of Tsakan and Zhang, that instead of minimizing abandonment, it would try to maximize this success probability, the probability that I would not close conversation before they were ended. And what we show in proposition 4 in the paper is that if the conversations are homogeneous in terms of their success probabilities, that indeed lowest load policy is optimal for very, very reasonable conditions on the service rate and the success probabilities. So basically, we can replicate the results of Tsakan and Zhang for a different performance measures. And again, the performance measure, which is the success probability, is related to the Hawks in the sense that we are measuring whether we are moving beyond when a conversation ended or not, so whether we succeeded or not, according to the Hawks process. So according to the probability that there will be another message in that conversation. Then what we are doing in the second stage is connecting this to homogeneity of the success probability to the closure. And what we do here is basically looking at this process, at the host process, and defining a stopping time. Basically in time where there was enough break between messages that we can call this conversation closed. We can regard this conversation as if it was closed. And we are proposing a hyperplane that depends on a weighted sum of the decay rates. And we propose that hyperplane, and we define a heating time to that hyperplane. And what we are showing in lemma 1 is that if you're closing the conversation at one of those hyperplanes, then basically what you are getting is a success probability that is homogeneous. But if, on the other hand, you're not doing that, then instead of getting a success probability that is homogeneous, what you're getting is heterogeneity in the success probabilities. And therefore, and the problem with what's going on in our data is that companies are not closing their conversations according to that heating time. But instead, what they're using is something very, very simple. They're waiting for 2 hours and then they close. Or some companies would wait only 2 minutes and then they close, which is very annoying to customers. And to show that what we are suggesting in our policy is actually what's fixing this problem, we're extending the previous problem in our stage 2 to the homogeneous case. So here we're just taking a very, very simple heterogeneous case in which the success probabilities is just have 2 probabilities, eta 1 with probability p and eta 2 with probability 1 minus p. Okay, and this is very, very simple extension to the success probabilities. And what we're showing is that if you're checking 2 policies, one is the lowest load, and the other one is something we call HP, which is basically prioritizing the lowest activity within the lowest level instead of just the lowest level. Then the performance of the lowest load would always be lower than the HP, and the HP is optimal. So once you have heterogeneity in the success probability, you have to take into account this heterogeneity in your prioritization. And this is exactly what our Hawks policy is doing. It's capturing this level that the system is in, and take this into account in the routing, and therefore takes into account the heterogeneity. So basically, a company can do one of 2 things. It can either close conversations according to the Hawks process, so according to the activity, and then it can use the lowest load routing, or it can do the opposite and adjust the routing policy to take into account the level of activity and use and close conversation however they want. And this is the reason that we are having such a good improvement when we are taking into account heterogeneity, because in our data, and the simulation was based on real data, the closure is after 2 hours for 30% of the conversations. Other 70% were closed either by the customer when it's ended or by the agent in a specific time. But 30% of the conversations, there is a deterministic 2-hour time in which until closure. Okay, I will skip this and the conclusion and answer questions because we are running out of time.
Thanks a lot, Galit, for the really nice talk. Indeed, we are out of time, but maybe we can take one last question from the audience. Anyone has a question?
I'm also willing to, if someone has more questions, I
Sure.
can stay.
Yeah. So I had, if no one else has a question, I had just one quick question about your SysPHP model. Is it, how do you estimate the sentiment? I mean, especially in chat, it's hard to gauge the emotion. In fact, in the chat you've shown us, I think you can read it in 2 different ways, and it depends how you read it, whether or not it's negative or positive. So I was just wondering,
Okay.
and I know you have other work on this, so how do you kind of
So
measure
with
sentiment?
GPT, it's becoming easier and easier in the sense that there are very, very good engines these days to estimate sentiment. Basically, what all of them are doing is have some dictionaries of words that are positive or negative, and then they are using analysis on the structure, the grammar of the sentence.
Okay.
And if there is an amplification, then it's the sentiment, whatever it's positive or negative, is increasing. If there is a negation, it's changing, flipping its positiveness to negativeness, etc. And so basically, it's an NLP kind of analysis on the text itself.
Okay, I see. Interesting. Any other questions? If not, let's thank Galit once more for the great talk and hope to see you all in the next SNAPP seminar.
Thank you.